The next addition reactions of carbonyl compounds we're going to talk about are those of organometallic reagents, adding to aldehydes and ketones, and then hydride, adding to organometallic, adding to aldehydes and ketones. Those are net reduction reactions because it converts the aldehyde or ketone into an alcohol. So let's start off with the organometallic reagents that you're already familiar with. Last semester we talked at some length about Grignard reagents, alkyl magnesium bromides being the most common, and organolithiums. And we talked about how those reagents are formed from their corresponding alkyl halides. The addition reactions of those are carried out under anhydrous conditions. So the Grignard reagent or the alkyl lithium, for reasons we talked about last semester, have to be made and handled under anhydrous conditions. Those can be reacted with aldehydes or ketones, and then in a workup that involves a little aqueous acid, the products isolated are alcohols. It's a very versatile way of making alcohols. You can form primary, secondary, and tertiary alcohols, depending upon the nature of the R groups indicated here, R1, R2, and R3. So you can imagine a lot of scenarios. If both R1 and R2 are hydrogens, then addition would produce a primary alcohol. If this is a simple aldehyde where R1 is an alkyl group and R2 is a hydrogen, then the addition of a second alkyl group would give a secondary alcohol. And if this is a ketone, the products would be tertiary alcohols. So here's an example. Note the way that these reactions are written. So here's a simple aldehyde. This is acetaldehyde reacting with this isopropyl magnesium bromide. And then when quenching with water, you end up with this secondary alcohol. Very synthetically important. It's carbon-carbon bond forming reaction. So the new carbon-carbon bond we formed is right here. So these are the two carbons that came from here, and then the three carbons that came from our isopropyl are there. So here we have butyl lithium, or we add a butyl group, and there's our butyl group, new carbon-carbon bond forming reaction. In this case, we end up with a tertiary alcohol. So these are mechanistically some of the simplest reactions that we deal with in this chapter. So let's write out the mechanism of this reaction. So here we have allyl magnesium bromide reacting with formaldehyde. And unlike the reactions we've seen previously, these reactions are generally not equilibria. These are reactions that go to completion. So the Grignard reagents, alkyl lithiums are strong nucleophiles, and so they're going to add quite readily to carbonyls. And form an alkoxide. This would exist in solution as its magnesium bromide salt. So the addition is just that single step, and that part of the reaction is done. That would exist in ether solution, and it has to take place under anhydrous conditions. We then add water, usually acidic water, because we need a proton source, so it's usually a dilute hydrochloric acid, and that simply protonates the alcohol. And that's our product. So those simple two steps. So let's look at some examples of how this can be used and the versatility of this reaction. So you can make primary alcohols from organometallic reagents and formaldehyde as your carbonyl compound. So this is formaldehyde. This is typically the way that one writes the condensed formula, CH2O. So that indicates that that is formaldehyde. So just to be clear here, we're talking about the reaction with, just like we did in our mechanism. So just to be kind of complete about everything, we make Grignard reagents, of course, under anhydrous conditions from corresponding alkyl halides. Here we have chlorocyclohexane. Here's the Grignard reagent. Treat that with formaldehyde, and then on quenching, we would add one carbon. That one carbon comes from the formaldehyde. So mechanistically, we get addition to the formaldehyde, and then we quench, we're protonating the alcohol. Sounds simple. It's actually not as simple as you think because of the nature of formaldehyde. Formaldehyde is a difficult compound to work with in the lab. It's also quite toxic. There are various forms of formaldehyde. You're probably most familiar with formaldehyde in the biology lab as a tissue fixative. In the chemistry lab, we use formaldehyde in different forms. There is a polymeric form of formaldehyde known as paraformaldehyde, and often using the paraformaldehyde gets around the problems posed with working with formaldehyde under anhydrous conditions. So it's not uncommon to see a reaction that looks like this. So what's happening in this reaction? You're probably thinking, well, wait a minute, what's going on here? Because there's an organolithium, and there's paraformaldehyde water. What is going on over here? We're actually deprotonating this compound. So there is a hydrogen here, and the butyllithium here is being used as a base. So it's butyllithium, and it's being used as a base to deprotonate that and form the acetylide ion. So what's being formed is this anion, be a lithium counterion. And that's our nucleophile. So that nucleophile is reacting with the paraformaldehyde compound. And so we end up adding that carbon to the end of the compound. So that's how you make primary alcohols. Secondary alcohols are made by the reaction of organometallics with ordinary aldehydes, where you have one alkyl group attached to the carbonyl. Generally speaking, when you look at a particular target that is a secondary alcohol, so here we have a secondary alcohol, there are really two possible synthetic routes. One synthetic route involves adding one alkyl group. So, for instance, we could add the methyl group to an aldehyde. But another synthetic route would involve adding another group to a different aldehyde. And so those two routes are shown here. On the left-hand side of this, we have, you notice this aldehyde, which represents the lower part of this molecule, and we add the methyl group to it in this case. The alternative synthesis would be an aldehyde formed from these two carbons and the oxygen, and then we add these three carbons to it, so it would be something like this. So generally, this is the kind of thing a synthetic chemist would spend some time researching before they went into the laboratory and chose one pathway over the other. It turns out if you do a little bit of research, you discover that this unsaturated aldehyde here on the left is commercially available, not terribly expensive. You can actually buy pre-made methyl magnesium chloride. On the right-hand side, it turns out this organometallic is not available either as an organolithium or as a Grignard reagent. So you would have to make it from the corresponding alkyl halide, and you'd have to look for that. And also this acetaldehyde, while it is commercially available, it's very difficult to get it dry because it forms a pretty stable hydrate. And so that poses a problem for that addition reaction. So if it's not dry, it's going to interfere with your organometallic. So if you were going to choose a pathway, you'd choose the one on the left as the one to explore first. Here's a couple more examples of the synthesis of secondary alcohols. These compounds are actually commercially important substrates that are used in the synthesis of various drugs. And in each case here, you can see that we have an aldehyde, an ordinary aldehyde. So here we have an aldehyde. Down here we have an ordinary aldehyde. In each case, we're adding different organometallic reagents to one or the other. But in each case, the aldehyde plus organometallic reagent yields a secondary alcohol. So here we've added the vinyl group using vinyl magnesium bromide. Here we've added this group to that aldehyde. So here's the group we've added using the corresponding organolithium. So secondary alcohols have typically two possible synthetic pathways to their formation. Tertiary alcohols, at least in theory, have three possible synthetic pathways that can be used to make the compound. So here's an example. Our target tertiary alcohol is shown here in the middle of the slide. So notice this is a tertiary alcohol. That's a tertiary carbon. And so we could have three different ketones and three different organometallic reagents that one could possibly employ. So for instance, if you look at this, that's a methyl group. So one could imagine adding a methyl group to a ketone where the ketone was at this carbon and the rest of the molecule are there, and that's what this is. So here's the cyclopropyl ring, here's the rest of the molecule, there's the ketone. If we add that methyl group, we end up with a tertiary alcohol. But you could also imagine adding a Grignard reagent that was a cyclopropyl Grignard reagent. This is actually a real compound. You can make this. But that would mean that the starting ketone would have to encompass the rest of the molecule, and there's that starting ketone. And then finally, you can imagine this chunk of the molecule as the organometallic reagent, and then this small ketone here that had the methyl group and the cyclopropyl. There's the ketone. Here's the Grignard reagent. And there's how you could make it from a corresponding starting material. So again, as a synthetic chemist, you would start doing some research and say, well, what can I buy? What is commercially available? What would I have to make myself in order to figure out which one of those pathways is the most commercially viable? At least theoretically, they all look perfectly fine as synthesis of a tertiary alcohol. So that's our look at the addition of organometallic reagents. Very versatile, can make all sorts of alcohols using that technique. And it is a very standard technique even today in the research laboratories. So another nucleophile that we can add to aldehydes and ketones is hydride, H-. And there are two fundamental ways to do this. One of those involves borohydrides and the other aluminum hydrides, and we'll talk about both of these separately. So let's start with the reduction of aldehydes or ketones using sodium borohydride. So this is a reduction because from an oxidation point of view, aldehydes and ketones are oxidized forms of alcohols. In order to effect the reduction, we need to add hydrogen across the double bond. This can be done by adding a hydride ion to the carbonyl carbon and then protonating the oxygen. Sodium borohydride is a very versatile reagent, very simple to use. It's a white crystalline solid, and it's compatible with water or alcohol solvents. And so you often see those reactions written simply like this: sodium borohydride in water or sodium borohydride in an alcohol. Here we have methanol. All right, so that's what the reaction looks like. Let's look at the mechanism. So it's actually pretty complex stoichiometry. In order to reduce a ketone to an alcohol, the stoichiometry is such that 4 equivalents of an aldehyde or ketone will react with a single equivalent of sodium borohydride. You need 4 equivalents of water. This could be alcohol too. And you'll end up with your alcohol, 4 equivalents, so we have mass balance. And the borohydride ends up as this borate salt over here. So let's work our way through the mechanism and see if we can account for everything that's going on. So the borohydride ion, which is BH4-, is a source of hydride. And so the first thing that happens is addition of hydride, it's a strong nucleophile to the carbonyl carbon. And that produces an alkoxide intermediate. Like so. That alkoxide is a strong Lewis base. And what remains from the borohydride is borane, which is a strong Lewis acid. Electron pair donor, electron pair acceptor. And so these things very rapidly form a complex. So after addition of hydride, the oxygen complexes with the boron. And that forms this borate ion. That borate ion can react with 3 more carbonyl compounds. So each one of these hydrides is available for reaction. So this can react, in fact, 3 more times with 3 more equivalents of our carbonyl compounds. So in this case, and it happens the same way. We get addition of hydride, and then the oxygen adds back to the boron. So what that leads to is this curious beast. And this is called a borate ester. These borate esters are actually unstable to water. And so as soon as they form, they react. And here's how that reaction occurs. There's a proton transfer to one of the oxygens that occurs. I'm going to abbreviate the remaining 3 of these as that. And then this leaves, like so. And so we end up with our alcohol and this borane. That continues to react, in this case with hydroxide. We formed hydroxide over here, by the way. That adds to the boron. Oops. And we're back to our borate ester. And it reacts 3 more times. In this case, with 3 more equivalents of water. Could be alcohol too. And so we got our remaining 3 equivalents of alcohol, and we end up forming this borate. So that's our mechanism for the reduction of an aldehyde or ketone using sodium borohydride. There are alternatives. Some aldehydes and ketones are kind of slow to react with borohydride, and we can use other reagents. One of the more important ones is lithium aluminum hydride. This is a stronger reagent. It does the same thing, but it's a more aggressive, stronger reagent, and so some compounds that are sluggish to react with sodium borohydride will react quite readily with lithium aluminum hydride. The other issue is that lithium aluminum hydride is not compatible with water, or alcohols for that matter. So there's an issue with these two that I'll get to on the next slide, and I'll kind of explain why you have to handle lithium aluminum hydride kind of the way that you would handle an organometallic reagent because of the way that it reacts. So you'll notice in these reactions, the way that they're indicated here, it's two steps. The reaction of the lithium aluminum hydride under anhydrous conditions, typically an ether solvent of some sort, diethyl ether or tetrahydrofuran are often used. And then, in a subsequent step, we add a little aqueous acid. The hydrogens in the compound come from two sources. The hydrogen that's added to the carbon of the carbonyl comes from the hydride, the lithium aluminum hydride. The hydrogen that ends up on the hydroxyl group actually comes from the water or acid that we add in a subsequent step. So here are two simple examples. This cyclobutanone is reduced to cyclobutanol. And here, this is retinal. Remember that? We talked about it previously. In the laboratory, you can reduce that to vitamin A or retinol using a lithium aluminum hydride reduction. So the mechanism is essentially the same as the sodium borohydride reduction, but as I said, you have to handle these things. You handle lithium aluminum hydride as if it were an organometallic reagent. So here's why. Sodium borohydride is somewhat compatible with water, but it does react slowly. And that reaction looks like this. If you were to just take some sodium borohydride in the laboratory and put it into, say, a beaker of water, you would get this very slow reaction, and it's visible. You can kind of see the visible effects of the reaction, where you end up forming this borate and hydrogen gas. And so what you would observe is fizzing. You'd see gas evolve from the reaction mixture. That happens very slowly, and it's only mildly exothermic. Same thing would happen if you use sodium borohydride in an alcohol. So if I put sodium borohydride and I were doing my reaction in methanol, again, you'd get this relatively slow fizzing that occurred. The sodium borohydride would react. You'd end up forming a borate. This is a slightly different borate. And you would get the evolution of hydrogen gas. And these reactions are just mildly exothermic. If you were to run it in a test tube and hold it in your hand, you'd probably feel a little bit of warmth, but not anything terrible. Here's the problem with lithium aluminum hydride. If you take it in the laboratory and you throw that into a little bit of water, this reaction, which looks very much the same, is very fast and very highly exothermic. So you form an aluminate salt, similar to the borate salt, and hydrogen gas. That reaction is highly exothermic and rapid. Why is that a problem? Well, that hydrogen that's evolved can mix with oxygen in the atmosphere, and because the reaction is releasing so much heat, you can get a fire. So this is similar to what happened when the Hindenburg exploded over New Jersey. And if you don't know what I mean by that, please look it up. So that's how you reduce compounds in the laboratory. So let's talk about something that's related to these things that we've been talking about here. Let's say in the laboratory you had a molecule that you wanted to synthesize, and that molecule is shown right here. It's this ketone tertiary alcohol molecule of some sort. And if you kind of say, all right, from a retrosynthetic point of view, how could I make that? You say, well, all right, well, we just learned how to make alcohols. One way to make alcohols is by a Grignard reaction, right? And so that Grignard reaction would look like this, where the Grignard adds to this ketone, forms this alkoxide intermediate, and then we protonate. But wait a minute, let's go back here. That's a Grignard adding to a ketone, but that Grignard itself actually has a ketone in it. So, well, wait a minute, how would you even make that? Because if you tried to make that organometallic reagent, it would add to itself and either form the four-membered ring, or one molecule would add to another and it would actually polymerize. So this compound is actually an impossible structure to make. You can't make this Grignard and expect it to stick around and not react with itself and wait for you to add in a different ketone. So how do we get around the problem? Here's that reaction, by the way. If you tried to make the Grignard, so here's the starting material that we would make this Grignard from. React that with magnesium, it forms the Grignard. But any of that compound that was unreacted, the Grignard would react with. And so now we've got these things connected together, and that's not what we want to make. So how do we figure out our way around the problem? Well, it turns out we can use some other chemistry that we've just learned about, and that is formation of acetals. So we can protect this ketone that's in this bromide by the formation of an acetal in the fashion that we talked about previously. So take an alcohol, or in this case a diol, and an acid catalyst. React those, probably under conditions where you azeotrope out the water. And now we have an acetal. And that's a perfectly stable compound. You can isolate that. But that's no longer a ketone. That's an ether for all intents and purposes. And ethers, well, they don't react with Grignard reagents. So I should be able to take that compound, react with magnesium, and form this stable Grignard reagent, because this is unreactive to Grignards. So if we form that compound, make the Grignard, we should be able to cleanly react that with this ketone, form the alkoxide from the addition of the Grignard reagent to the ketone, which exists as this salt, and then we add acid. And when we add acid, not one, but actually two things are going to happen. One, we'll protonate that oxygen, right, and make our tertiary alcohol, and there's our product. But remember, aqueous acid reverses the formation of an acetal, and so that acetal will come off at this point, and that's perfectly fine because we no longer have the Grignard reagent around, and there's our product. So that's what's called using a protecting group. We've protected the ketone to reaction with a Grignard reagent, and then we were able to reveal that later on. There are other aspects of this that are important too. These strongly nucleophilic reagents, such as Grignard reagents or organolithiums, are also strong bases. And so if we want to react, for instance, something like an organolithium with certain compounds, you remember from last semester that these will react with protic functional groups. So if I wanted to do this substitution reaction where I want this organolithium to displace this bromine by an SN2 and form this alkyne, then I can't do it if there's an alcohol in a molecule, because I'm going to get the acid-base reaction first. So how do we get around the problem? And the answer is we need to protect. We need to modify that alcohol group temporarily and turn it into something that won't interfere with our reaction, and then be able to remove that protecting group. So here's another way to do that. You can convert an alcohols in the laboratory into siloxanes. So you can protect them with a silyl protecting group, and these are done with these silyl halide compounds. Alcohols are nucleophiles. Silicon can undergo SN2 reactions. You get an SN2 reaction where the oxygen displaces the chlorine, and you end up with a silicon-oxygen bond. So now it's no longer protic, and I can react it with more organolithium. It only reacts here. We form that product, and then we can take that protecting group off. And there are a couple different ways of doing it. One way of taking that protecting group off is to treat it with fluoride ion. There are many sources of fluoride ion, but to do this safely, the most common one is tetrabutyl ammonium fluoride. It's a soluble fluoride salt. Fluorine has a very high attraction to silicon because silicon-fluorine bonds are quite strong. And so it will actually do the substitution, and the oxygen is kicked out, subsequently protonated, and we get our alcohol back. Also, silicon-oxygen bonds are prone to acidic hydrolysis. So if we just add acid the oxygen will be protonated, and water will do the substitution for us, and we can get back our alcohol. So the combination of the putting the silo group on, doing it, and then taking the silo group off means we've been able to protect that alcohol from reaction. There are other ways of doing this, or other protecting groups. For instance, you can convert alcohols into tetrahydropyranyl groups. So this is an alternative to using the trialkyl siloethers. This is dihydropyran, and in the presence of an acid catalyst, it reacts with alcohols. Here's how that works. So in the box, under acidic conditions, dihydropyran is protonated. It protonates at this position, forms this double-bonded oxonium ion, which kind of acts like a carbonyl. Alcohol will add to it, and then deprotonation, we end up with this. And that's really nothing more than an acetal. And acetals don't react with strong nucleophiles. So in this example that we see here, the reaction we want to do is we want to reduce this ester group to an alcohol. But it turns out you can't do that with lithium aluminum hydride if you have an alcohol already present. The alcohol, of course, would react with the lithium aluminum hydride, and we'd probably get an explosion or a fire. But reacting the alcohol with the dihydropyran converts it temporarily into the THP group, and then we can do our reduction reaction, and then acidic hydrolysis can remove that THP group. So just to summarize those protecting groups, because I really talked about three, acetals can be used to protect aldehydes and ketones, and they're done by forming the acetal. Cyclic acetals are better than acyclic, so this is one of the more common ones. And we are protecting them from reaction from other nucleophiles and bases. So to do the protection, you need a diol and an acid catalyst. To deprotect, just a little aqueous water. Trialkyl silo groups are used to protect alcohols. The form of those look like this. And again, we're protecting them from nucleophiles and bases. In order to put the silo group onto the alcohol, you just need a silo chloride and a base. And to deprotect, to take it off, you either need aqueous acid or fluoride ion. And then finally, another way of protecting alcohols is as tetrahydropyranyl groups. It looks like that. It protects alcohols in general from strong bases and nucleophiles. To put it on, you need dihydropyran and an acid catalyst. To take it off, just a little aqueous acid. And so we have these tools that allow us to work around some fundamental problems in doing synthesis. And that completes this section.